All right, I wanted to go ahead and go through an example of an application where partial fractions get used. But I'm not going to really show the partial fraction part. This is very similar to when we discussed exponential growth and decay, in which this is a little bit more algebra than calculus, even though the notation we'll be using is calculus notation. So this is logistic growth, and logistic growth is growth that starts exponentially but then levels off. So it's growing faster and faster and faster the more there is, but then it reaches what's called carrying capacity, which is a horizontal asymptote where our growth levels off. This is much more typical of population growth, where due to environmental factors, only a certain population, a maximum population, can be supported due to food, water, that type of thing. And the equation for it is a bit different than exponential. If you remember exponential, if I use p for population, the rate of change of the population would be some constant times the population. With logistic, the rate of change is still some constant times the population, but then I have another factor here where m minus p, where m is the carrying capacity and p is also still the population, but m is this maximum that it could have. And I've seen this occasionally on AP tests, but it's never been asking you to solve this. It's been more of asking questions about, do you recognize this as logistic? And so kind of an example of what this would go through, and this one's in your book, is, let's say the growth rate of a population of bears is modeled by dp dt equals 0.008p times 100 minus p. So the 0.008 would be the k, p would be my population, and 100 would be the m. And so if you recognize that this is logistic growth, the carrying capacity then is very quick and apparent in that it's 100 bears. If you don't recognize that this is logistic growth, you'd have to go through all of the steps of solving this differential equation, finding the function it comes from, finding the horizontal asymptote for it as p goes off towards infinity, or as t goes off towards infinity, and it's a lot more work. Uh, Now, the parts B and C are a little bit more interesting in that if we notice, this is really a quadratic, because if I multiply this all out and get rid of the parentheses, I'd have a p squared term. So if I graph this as my p value is the x-axis and the y value is the dp dt by rate of change, I get a parabola. And at the vertex is where my maximum rate is. So the bear population, when it's growing the fastest, is right here. And if you notice, it's half of our carrying capacity. And this is always true in that if we recognize we have logistic growth, instead of finding the actual equation, if they ask us what's the bear population, what's growing fastest, it's always half of m, because of the fact we're dealing with a parabola in terms of p. And then to figure out what that actual rate of change is, I just plug that in for p, and I would get 20 bears per year. Now, if we were to actually solve this, I'd have to move all the p's over to the left side, move all my t's to the right, and I would have to be using partial fractions. If you're interested in seeing where it all comes from, on page, an example on page 370 in your book goes through all of the steps of solving it with partial fractions. I'm not going to go through it all here. But you end up with a function that looks like the carrying capacity over 1 plus some constant a that depends on the initial condition times e to the negative mkt. And you're free to look at that if you choose to. However, that. I've never seen them ask you to actually find this function. It's always been, given this differential equation, if you recognize it's logistic, the questions go much faster.